Okay, so let's a little bit about me. So yeah, I represent here both JetBrains and DevExpress. So I worked for 15 years at DevExpress doing high performance trading software. That's where, while working there, I has actually started teaching course on concurrent distributed programming in ITMO, just because we needed it in practice, and there was not enough students with the knowledge of the whole theory. Now I represent DevExpress board here as a sponsor of this event, and but for the last year I work full time at JetBrains on the new Kotlin language, and that's be related to my today's talk. So what we're going to talk today about? First of all, I'll give you a short overview. What's the Kotlin language? What's Kotlin Coroutines? And we'll try to motivate you. Why do we need log-free algorithms there? I mean, I'm a practitioner, more practitioner than I'm not an academic. Even though I teach at university, I don't publish any research. Even though I speak at technical conferences, and for me, it's always even when it's purely theoretical stuff is presented, I always seek to understand, why. And that's what I start with, give you some motivation. Why do we need log-free at all? Why don't we just do locking or whatever, or do some other techniques and live with it? So we'll talk about two algorithms. First will be log-free double linked list by Sandel and Siegel. This is pretty complex algorithm, and my goal for this lecture is not going to be so you can walk away and write it down. Don't worry, there will be no code. There will be no slides filled with code, only like in the motivation part, but not the actual algorithms. My goal for this presentation is so you understand the feel, so you can start feeling why it works and how it works, not to understand at the level that you can actually go ahead and write it, but to understand general concept that underlie the whole construction in this algorithm. And our second algorithm will be log-free multi-word compare and swap, and this one is actually simple. It's extremely useful and very simple, and I hope that after listening that you will actually be able to sit down and implement this algorithm, because once you understand it, it's pretty straightforward. You don't have to pick into paper. Like once you understand how it works, it's pretty straightforward. Just sit down and write the code. And the reason both these two algorithms, and that's kind of a key scheme of this topic, we'll see on a couple of examples how we can combine those. This is both two algorithms of our just published papers. And we'll see how we can combine them to do more complex atomic operations that are still practical and efficient without going full software transactional memory. And if we have time, we can talk why if we use STM, that would be much less efficient for those particular cases. But in this, we're kind of lucky, so we have a practical problem, and the first part, I'll tell you what the practical problem is. We need algorithms, and existing kind of state allows us to pick and combine them so that we get what we need. So let's get started. So Kotlin, what's Kotlin? Kotlin is a JVM language developed by JetBrains. Was designed to be, started in 2010, designed to be Java replacement, general purpose language, statically typed, lots of, like other languages. It's was both object-oriented functional paradigms. It's open source under like Apache 2.0. It's was released as 1.0. So it was been working on 6 years. In 2016, it was mature enough, tried enough to be declared 1.0, and now there's commitment to maintain backwards compatibility. Now it's version 1.1, which is still compatible with 1.0, and it has been recently officially supported by Google on Android as additional to Java, which kind of is a big win for this language. So, again, it's not about Kotlin, but to get you a little bit. So Kotlin is, first of all, is a modern language. It was designed around 2010, and it's really similar in feel to other language designed around that time. So it's really, you can see that it's concise. So the code you get, you write less code, it get more substance. It's concentrated on safety. It has null safety. It has features that lets you, and type safety is, of course, important. It's extensible. You can write your own DSLs, and it's, first of all, pragmatic. Like it's designed by practitioners for practitioners to make developers' life's easy, and lots of developers actually fall in love with the language. It's fast to work with. They write, blogs saying how they love, Kotlin, how it made their lives easy. So it is pragmatic. And it's quite easy to learn, especially for Java developers. Java developers will pick it up in day 2. So we'll have a bits of Kotlin code, and even if you've never seen it, you'll understand what's going on. So we won't spend any further time. So the coroutines was added quite recently to Kotlin 1.1. The coroutines are needed for asynchronous programming. So what's coroutines and what's asynchronous programming? So the key problem is, how do you write code that waits most of the time? Like, that's unfortunately, that's the modern world we live in. Lots of modern architectures involve lots of third-party services, lots of network communication. In the modern world, you wouldn't have seen this like 20 years ago, but nowadays, you'll see that, lots of modern applications, they spend most of the time waiting for something. They made a network request to some service, they wait for an answer. They made another request, wait for another answer. That's a common pattern nowadays. Like, the modern code waits a lot. And a traditional approach to this was that you do this by blocking thread. You write your code as do 1, do 2, do 3, and each request to some other service would block your thread. And each worked great 20 years ago, 10 years ago. But now, the problem is, nowadays the architecture became so, like this is the whole microservices approach, that, how many threads you can have? You can have 100, you can have 1,000, for example, on the back end. But what does it mean? If I have 100 threads and one of my backend services is slow, I can quickly get all my 100 threads waiting for the answer from that service, and the system as a whole doesn't do any progress, even though resources are clearly not used. So people invented lots of workarounds to solve this problem. So that's kind of clear problem in modern times. All this was blocked, waiting for something. And the first thing people started to use is callbacks, right? So instead of doing like your nice sequential code, you do asynchronous requests. This is called asynchronous programming. So you start operation, but your thread is not blocked. When it's over, you serve callback, then you can do another callback, and this leads to a thing called callback hell. Like lots of those, callbacks one inside another. So the people invented the other approach, which is a very old approach. It's futures, promises, and a Rex library uses this too, is instead of like doing callbacks, you compose multiple steps with different combinators. This is better, but it's still like your code stops looking natural. So basically, you end up writing your asynchronous code in a completely different style from your regular synchronous code. So the coroutines is the answer. It's actually a really old answer. The concept was like for 15 years. 50 years ago was the first big language that used coroutines. In that you write code as if it is sequential, but the compiler actually compiles in a way that's asynchronous. So while some operation waits, the thread is actually released, and you can use it for something else. So that's what coroutines is about. That's why we need them in the modern world, because we write lots of software that, instead of doing stuff, waits most of the time. And also, this kind of promotes a whole different style of programming. There is CSP, communicating sequential processors, and closely related actor model to it. That's the whole style of building software that encourage you to split your task to lots of small tasks that communicate a lot, and they wait, of course, each other a lot. So, if you're like full actor model, you can have hundreds, thousands, millions of actors in your systems, and they communicate all the time. And instead of sharing data, they share data by communicating. So this, of course, also promotes immutability. So you don't mutate shared state, which is complex, mutating shared state, locking, data races, we've heard all that. It's hard to share the same data structure. So it can promote shared data by communicating style where you, instead of sharing data, you just send data from one actor or from one task or agent to another. So in order to enable this, we need to give programmers primitives. Like we, as in people who write Kotlin. So we have a language that has basic support coroutines, but we also need to write support libraries. We need to give people like ability to future, so you can start a task and then wait for its completion later. We also need to give them channels, so you can send data into the channels and receive from the other task. We need both synchronous channels and buffered channels. We need the ability to select or to provide alternatives where you can wait for multiple events and then do something depending on it. We have to support cancellation because, on timeout, basically, if my request times out, I need to cancel, cleanly stop listening for whatever I was waiting for. We need to support like parent-child relationships so I can build like actor or my agent hierarchy stuff. That's all the low-level stuff we have to give developers so they can write in these styles. And the problem is that, okay, so we now have to implement all of that. And here are our challenges. Like, one thing is implementing all those primitives for threads, but we're implementing these primitives for coroutines. And coroutines are conceptually like very, very lightweight threads. The difference is this: you can have a few thousand threads. Each thread is a big thing, like 2 megabytes of memory. You can have tens, 100,000 threads. But coroutines are so lightweight, you can have millions of them. And it means that all the low-level mechanism that we design for the coroutine have to scale to this scale. Like, it completely changes requirements that are being, being attached to all those level communication primitive, because like if we're doing like logs for threads, we know we're not going to have too many threads. So we know like our wait list can be too large because we don't know number of threads limited. With coroutines, we have to always think, what if there are a million coroutines wait for this event? What do we do? And stuff like that. So it has to scale because the coroutines are so lightweight. And so I'm going to do hand waving here because that's where we need log-free algorithms. That's really, log-free algorithms, they're also about scalability. That's the whole point. Like log-free algorithms, they let your code scale. So you have more cores and you're still not running into too many contentions because you have less of those serial bottlenecks in log-free algorithms. And also log-free algorithms that we'll be using are mostly disjoint-access parallel. So if my different parts of my system don't work with different structures, we don't run into any contention at all. And to implement all those primitives, we'll be that's about line. We'll be using the following building blocks. Our building blocks first building block is going to single word concurrent set operation because that's all we have in GVM. Even though processors support modern processors support wider concurrent set, but like every Intel processor has an instruction to concurrent set to neighboring words. But the GVM that's we're targeting as our compilation target supports only single word concurrent set. We're also using automatic memory management. That's its garbage collection. And I will use this forum where so many researchers from different places here to complain about a little bit about the state of art in data structure research, because when I, as a practitioner, start reading a paper on a very nice algorithms, I don't care about all the memory management aspects, and nobody actually cares because most code nowadays is written with some form of automatic memory management. So when I open a paper and I see this really nice and novel algorithms that nobody has figured out before, and its code and presentation is riddled with memory management aspects, like the whole logic is obscured by the presentation about memory management, I start to cry. Why couldn't you just present your algorithm separately from memory management? Why do I care? There's so many generic memory management techniques that I can apply to algorithm. Why do you write your paper with some specific memory management applied to it? I don't care. The only thing I care when I read paper about your novel algorithm is what the algorithm does, not how it manages memory. It's a completely irrelevant aspect. Just because, again, most of the time in practice, we have some automated memory management anyway. And of course, we're interested in practical log-free algorithms. Not every log-free algorithm that's published is practical enough. Have a low enough overhead and outperforms log-based data structures. And the two algorithms that we're using as building blocks, and on presenting algorithms, I'll explain why those two in particular, is the first one is log-free double linked list by Sandel and Sigas, and they have a series of papers with different modifications on that. And the multi-word compare and swap by Harris, Fraser, and Pratt. That's the two building blocks that core algorithms that will enable us to implement all those things that we want to get implemented. And automatic memory management, yes, that's the key. Those both papers, I mean, they're really bad in the sense that because you have to wade through them. You have to really figure out what's the algorithm doing and ignore all the memory measures. It's really hard to read because of that. So double linked list. That's going to be first thing that we'll be doing. The reason we need double linked list is because, again, why wouldn't we be okay with single linked list? I mean, if you look at Java, for example, lots of Java's concurrent building blocks are designed using single linked list, or some weak double linked lists. The reason is, for example, in Java, if you submit a future into a thread pool and then cancel it later, the memory gets reclaimed only when it's only marked as deleted, and some weak attempt to remove it in some certain cases is done, but it's basically stuck marked as deleted, and then at some point in the future, execution thread comes to it, sees that it's deleted and skips it. With coroutines, we can't do it because with coroutines, we have to be prepared for the case where there will be some long operation, everybody's waiting on it, but lots of coroutines, and they all time out. And coroutines are cheap; they can get started and cheaply thrown away. So we can have a case where millions and millions of coroutines have tried to wait, but then decided to abandon their way. So we really need double linked list so we can cleanly unlink any record. So for double linked list, we'll be using that's Sandel's and Thigas algorithm. The way it's described is with two sentinel nodes. So to the left we'll have at the head a sentinel node that never changes, and to the right we'll have a sentinel node that never changes. It's always there. The key idea of Sandel and Thigas algorithm is that the logical contents of the list will be formed by the sequence of next links. Like links on the left-hand side from to previous nodes will only serve to help us remove elements and find previous elements. They will be auxiliary data structure. But the next links will form the actual logical contents of the list. That's kind of the key central theme of the whole algorithm, that next links are central and previous links just auxiliary. In practice, though, it's interesting how what you read in scientific paper is different from what you will go to actually implement. There's zero reason to have two different sentinel nodes. In practice, we'll just combine them. So I will present all algorithms as they're presented by Sandel and Thigas with two sentinel nodes. But in practice, I mean, it's just one object that's both left sentinel and right sentinel. Instead of having two links to head and tail, we'll just have one link on the queue. So to get a feel how this algorithm works, I'll show how it works for a few simple operations first, and then we'll see how it takes care about cases when multiple operations are performed concurrently. So our first operation is insert. So we have to be able to insert on the right-hand side new element. So we first create it and initialize in previous and next links, and then we have to actually link it into the list. In order to find the previous element, we use the link from the last sentinel to the left, and then that's used to initialize our previous link in our node. Then we do compare and set, one atomic operation that changes in first node the next link, and that's it. That's the moment where operation has taken effect. Now the chain of next links includes element number 2, and everything the algorithm does after that is just helping fix the other references. Now this is the point where operation has taken effect. So if we failed in case, we just retry, reinit, and do it again. And there is a helping procedure that would help us finish insert, which correct the previous link. It also uses cast, just in case somebody else, some other thread interfered and also already corrected it. And because it's just a helping move, it ignores failures for cast separation. That's it. Insert is really straightforward. Insert on the right, like in queue, in queuing element, is really simple. Removing is on the left-hand side, like we'll need a queue out of it, so we'll need to remove element from the left, is not that straightforward. Yeah. The second one is for this particular non-contended insert, we just try to cast previous links from last sentinel to the second node. That's it. We just try. I mean, if it fails, we know somebody else is adding, and it will take care to correct the previous links. I mean, for the insert is really simple logic. We just try to cast previous link to the newly inserted node, and if cast fails, okay, we know somebody else is doing modification, and it will be that thread's responsibility to correct all the previous links. That's it. For remove is not that straightforward. For remove, let's see how remove works. So first of all, we need to find the first element. So we'll follow the green pointer to the first node. That's how we find node that's to be removed. The remove is done using so-called mark bits, right? So we would, instead of physically removing, we do two-step remove. And you've seen this, there was, I believe, on Monday and Tuesday. You've seen that's a pretty common technique in linking data structures. So this two-step remove, you first mark the pointer, then you do physical remove. So that's how it does here. So I mark remove node's next link first. This mark is the moment when the node is considered to be removed. It's still linked into the chain, but it's considered removed as soon as this marking comparing set succeeds. If it fails, we retry the whole operation. Navigate, the first node again, and retry, attempt to mark it as removed. In practice, we don't have mark bits. JVM doesn't support them. I mean, no managed language does. So it's not just JVM's limitation. So no managed language does support those mark bits. So in practice, we just use wrapper object that continues to point into the whatever it was pointing before. It's just we can distinguish it by a separate type. And we never use atomic markable reference in practice, though. So whenever you see somebody telling you a slide, use it, never use it. You should never be using it, because inside it implemented just the same way. So if you go to the source code of atomic markable reference in Java, it's actually implemented with this wrapper object approach, because there is no other way to implement it in managed language. But it's really cumbersome to use, and you can do optimizations, because we can actually cache those objects, because when we remove the link from first node to the following sentinel, we have to replace it with the removed object that's still pointing to sentinel, and we'll often do this as QLives. We can reuse this removed node pointed to sentinel object again and again. We don't have to allocate it every time. So having marked this, we need to mark the previous node too. So previous node is also the first step in removing, in continuing remove, and actually proceeding to physically remove the node is to mark the reference to previous node. But that's not it. Now we have to physically unlink the node from the list. It's done in two more steps. The first, and we'll retry this marking on failure, because we have to do it until it gets marked, then we'll correct the next link. This is operation called helping remove. Why is helping remove? Because if some other threads encounters in the data structure in previous state, it will help to work this next to a reference from previous object around removed object, and they will also correct previous reference. These are two helping operations. I won't go into the details of their logic. This is the most complex part of the Sunderland-Stiglitz algorithm, is how this helping works. Fortunately, we don't have to really understand how helping scheme works in order to use this algorithm in the larger scheme of things. All we really care about is where does the operation takes effect, and in particular removal takes effect, at the moment where it's marked. The other way to look at this algorithm is to look at its state transition diagram. So let's take on a node as a separate object. Let's see what states a node in this algorithm transitions through. The first state is when the node just created. No other thread knows it. It's completely local to the thread. It has next and previous links initialized, and it's not linked to the structure yet. Nodes around it are not pointing to it. Then we start inserting it with the first cast, and that's actually where node is considered inserted. So as soon as this cast succeeds, node becomes visible from outside. And either we or some other threads will move it to subsequent third step, whereas node is both locally and physically inserted, and both the following node's previous link points to this node, and the previous node next link points into this node. And the node will live in this state for a while. It's like regular state. The node is in the list until it gets removed. And the removal, as we see, starts with marking next reference as removed. That's the first step. As soon as this cast operation succeeds, that's it. It is considered to be logically removed. Nobody will see it in the data structure anymore. But it's not yet physically removed. And either originating thread or some other thread will help this node transition through the following state. So it will mark previous reference, having seen that next is marked, and it will correct next references around this node, and it will correct previous references around this. And at this stage, at step number 7, that's it. Node is no longer physically in the list. The key about this diagram is it's linear. It's not the key about linear. It doesn't have any cycles. So the node, we never reuse node objects, right? Never. Reclamation of the memory is not our care. Is memory management algorithm takes care when we can reclaim and reuse the memory. The node itself never reused, and this is a key. This is a common theme in all advanced log-free algorithms. All advanced log-free algorithms work by helping, where the one thread help another thread, and they are enabled by the fact that the state diagram does not have any cycles. So there's never a confusion what to do next. If we encounter a node in some step, we always know what to do next with it. And that's the key. That's the key to understanding how log-free algorithms works. They have a few like physical transitions, and the rest is just helping. And any thread can come, see that the node needs help, and move it forward in this state diagram. There's never confusion. There's no loops in this diagram, and that's the key. As soon as if we try to reuse nodes, that's it. There's no way we can make algorithm log-free anymore. So let's talk more about helping. How does this helping work? In order to understand how helping work, I will present a few examples, actual examples how when we have a concurrent operations, threads help each other. So first scenario is concurrent insert. So let's see, we have two threads. One is trying to insert node 2 and the other node 3. They both prepared to insert. They both created nodes tentatively with the probably, but they're not. Neither 2 neither 3 are yet inserted into data structure. The link of next chains that is in bold, in bold blue is still pointing, this way. So this is logical contents of the data structure. These nodes are still not there. So assume the node that inserts 2 moves first. It manages to cast a reference to itself, and the other node fails. It also tries to cast, but fails. It means that now node 2 is inserted. It means this thread won the race, and node 2 became inserted. But it's only logical inserted, not physical in data structure yet. Now, what happens if the thread that has just made this move, the second one, it gets preempted by operating system, whatever slips. Let's see what the other one does in this case. It will, on failing cast, it will reread previous pointer to see where it can be inserted, and it will actually check the necklace, and we'll see that it's inconsistent. Previous point here, but the next is pointing somewhere else. So it will launch the corresponding correcting procedure that would correct previous reference to where it should be. Now, having corrected previous, it can reinitialize itself, and retry its insert operation, which will succeed unless somebody else interferes. You know, it can, I mean, it's not a wait for algorithms. I mean, this particular guy, the guy number 3, can retry. I mean, it can always lose the other threads, but it's a lock-free algorithms. Because of the helping that goes linear in the state diagram, it's easy to prove that it's lock-free. Now, what happens if we have concurrent remove? Like, we have a list with 2 nodes, and we're trying to, 2 threads trying to remove an item. The first thread takes the first move, says marks it is removed, the first item. But that's it, and then it gets, say, preempted. The only thing it managed to do is to mark. Then the other thread comes in, you know, and see that's, oh my god, this next pointer, all the marker is removed. I cannot do it anymore. But so it has to help the other thread to finish operation. So it does marking previous and help remove operation, which, you know, corrects previous next pointer around the remove node. Then it can retry. Now, having helped to remove this element, the second thread can retry its operation, now follow corrected next pointer to the second node, and retry with the corrected next. And this one, at this time it will succeed, you know, remove the second node, and when it finishes removing, it will launch a procedure that corrects, that helps remove again, because it just removed itself, and then it will launch procedure to correct previous reference. That will actually scan the data structure to the left to the first non-removed node, and will you know, find the first non-removed before this chain, and we'll put a pointer there. That's it. Remove is complete. We have data structure where both nodes are, you know, both logically and physically removed. Let's see what happens if we have concurrent insert and remove. And the first case will be when remove is first and it wins. So we have one node that wants to insert a node, and the other node that wants to remove this node and insert after this node. If remover moves first, then the second node and then gets preempted. Then the node that tries to insert will fail its case. Why will it fail its case? Because this mark bit is combined with the pointer, because remover just replaced this reference with the reference to another wrapper object. So this thread will try to cast the old reference to itself, will fail because this next reference now has a different value. That's the essence of why we mark the node first. And by the way, as an interesting thing to think about those marks is marks mean do not modify this pointer anymore. Like the marked reference will never get modified. That's it. It's a final state for the reference when it's marked. And then inserter will retry, but when you're trying, it will see, oh my god, something wrong. So previous node points here, but it's removed. So because it will see it removed, it will launch a correct previous procedure that will help, not correct previous, but will launch the helping remove procedure that will finish marking this previous record, work around next, and then update previous, and that's it. It had helped the state of the structure to become physically correct, and now it can proceed to actual insertion. It will rename itself, and proceed to insertion. The other case is just as simple. We'll quickly go through it to save time for fun stuff later on. So when there's concurrent remove and insert, the same things with ready, but inserter wins. So remover comes in and successfully mark just changed reference. So okay, but then it will invoke processor to finish the process, to mark previous, correct next reference that will point to second node, and the correct previous, and that's it. Remove is over. It's interesting thing is that remove is over, but the data structure still is not a final state. So remove is done. It did complete its remove, but this thread that was doing insertion is preempted. It will wake up at a certain point and will will correct this previous reference. Or some other threads that comes to see this data structure in inconsistent state will come and fix this previous reference. At some point it will happen. And again, it's all possible because the state transition on every node is linear, left to right. There's no loops. Any thread that comes in can see what's wrong and can help transition node to the subsequent state. So let's put a not a break, but let's do important summaries here at this point. So what are our takeaways? First of all, this is kind of algorithms that you really need a scientific paper for. You will not be able, even if you understand how it all works, I doubt you'll be able to sit down and implement it correctly on the first try. Because especially the helping procedure is pretty elaborate here. You have to make sure, you have to remember about all the corner cases, if this removed, not removed, checking marks. It's pretty complicated piece of code. So that's where having a research paper with a proof, with a code really helps. You can sit down, take this paper, translate the paper into the actual code, and it works. And that's really helpful. And it's hard to improve without writing another paper. I mean, you see, oh my God, this is probably, we probably don't need this. Let's remove it. Oh, it stops working. So, I mean, that's really, and that's where we can have a progress. Like, why do we need to mark previous reference to? It's needed in helping procedure. Can we design an algorithm that doesn't do this mark and saves one case? I don't know. Maybe yes, maybe no. That's an open research question where it can be improved and this state transition diagram can be made shorter. Good news though, that if you mess up implementing it, forget something, it usually gets uncovered by stress test. So when you start, excuse me. No, because it's just boilerplate. I mean, they shouldn't have included it into paper. It doesn't bring any value, additional scientific value to the algorithm. It's just boilerplate. You can remove and insert it without thinking. You don't have to understand how algorithm works in order to apply memory management scheme to it. Because all the memory management heapful externalities, they're universal. I mean, there's a bunch of papers on how you manage memory in log files. They're all universal. You can apply any of them to any algorithm. You don't have to understand even how algorithm works most of the time. Rarely you can encounter algorithm-specific memory management schemes, but this is not the case. I mean, what's memory management? It's here, well, I get memory here, we're okay to release it. Okay, you just remove, we don't need, get set will come and go. I mean, that's it. If they use this, I mean, it's usually easy to remove, but it's like a effort. I would have preferred if they written it algorithm separately, of course, from the memory management. So the point I wanted to stress that if you, you have to really stress to find the bugs. Like you have to create short lists, do lots of concurrent operations, and in order to uncover cases where it fails or doesn't do something correctly. The bad news is when stress fails, you are up to sitting long hours, because if you implement algorithm, runs through stress, doesn't work. It crashes or hangs. Oh my God, you're bound to spend at least a day trying to figure out what's going on. It's never easy. More bad news is if you accidentally make a bug that violates log freedom of algorithm, they're almost impossible to find. And it's very easy to do these bugs in log-free algorithms. Like you forgot how this kind of log algorithm is structured. And most log algorithms are structured like this. It's a loop. You loop, we read something, try cast, fail, retry. And sometimes when you fail cast, you have to help. You have not to forget to help transition data structure to next state. If you forgot this helping move, algorithm still works. It's still correct algorithm. I mean, it will just loop in the data until somebody else comes in and help complete this operation. It just ceased to become, it just lost its log freedom property. And you won't ever find this kind of fucking stress test because all tests pass, but it's not, it works, but not log free. So this is where you have to really read through code and make sure take a careful look at every loop and convince yourself that you cannot be looping forever here. That you're making progress. You're not just waiting for something to be done by some other thread. Like if you've failed and retry, the code to correct the failure has to be in your thread. You should not be waiting for other thread to correct this problem. Or this is just log-based algorithm. So let's summarize what this algorithm lets us to do. So we can insert item at the end of the queue. We can remove it at the front of the queue. We can traverse the list because we always have a list of next links. And we can, what's important, we can remove items at arbitrary locations. That's what we need. Not just remove, we can do it in O1. That's what I'm taking at the beginning. We really need double linked list because we can remove an item, not just from the fork. We can apply the same algorithm to remove an item from any location in the list. And this is O1. And if you think about the scale of coroutine, this is very important because you can easily have millions of coroutines waiting for something. And if they all time out, they cannot use an algorithm to remove themselves. It will be n squared for a million. That's too much. I mean, they have to be, when they time out, they have to be removing themselves from the wait list in, quickly. Yes? Traversing is easy. It depends on whether you want to, what kind of, there are two kinds of traversals. One kind of traversal is that you would traverse just next reference, and then it's your decision whether you will consider nodes with marked as removed and ignore them, they're not there, or well, it depends on what you want to do in traversal. I mean, you can, but the next links always lead you from left to right, because we insert only on the right and remove only to the left, you'll never get lost. There is never loops, and even if the data structure changes while you traverse, you will always do, I mean, you are not getting a snapshot of the list. Definitely when you traverse, not. You will not produce an atomic snapshot of the list, but you can safely traverse it from left to right. We don't have to. We can, but we don't have to. We can help if we see, for example, remove node help, but we really don't have to. Because if we traverse from left to right, especially all we care about next links, which are, that's where we traverse the reference, that's all you represent the logical, that's where logical state of the structure is always equal to physical, the next links. And traversing left to right, the next links is the only thing we need. We can, but then if we traverse west, we have to always help. So traversing backwards, also implementable, will be much slower because we'll have to always check that it's correct and help if we encounter some problems. I mean, the full paper of Sigas and Sandel, they actually present the algorithm to back traversals. It's just we don't need it in our case. We're using it just as a queue, and we need only left to right traversal. So that's what we can do. And it's all the operations are linearizable, except traversal, which does not. Yeah, excuse me. Which one? This one? Yes. Because when you remove an item, all you do when you remove an item, even if it's arbitrary item, if you know the key is you can keep a reference to a node. Like if I have a list, I can keep a reference to a node. I don't have to find it. I can keep a physical reference. And then when I know, I don't even have to follow to find this node. I start by marking its next pointer and then help finish the remove. That's it. That gets me a O1 removal. Yeah, thanks. That was a good question. Yes.